Hi guys, welcome to this very useful revision video. We're going to be going through a real life exam paper. We're going through the GCSE Chemistry higher tier paper 1 of the AQA exam paper. So follow along, see how you do on a real life exam paper. We're going to be going through the whole paper and giving you guys tips on how to approach questions and how to make sure that you get the maximum possible marks. So let's dive straight into it. So question 1 then, this question is about metals and non-metals. So figure 1 shows an outline of parts of the periodic table. So we should all be familiar with the periodic table by now, but you'd also have the data sheet which would give you a periodic table as well that you can refer to. We're told that element Q is a dull solid, has a melting point of 44 degrees and it does not conduct electricity, and we want to say which area of the periodic table is element Q most likely to fall under. With these multiple choice questions, it can be useful to actually eliminate some answers straight off the bat. So we know that it's a dull solid, melting point which is quite low, doesn't conduct electricity. Straight away we can say it's probably not going to be a metal. Metals generally are much shinier, they do conduct electricity and they do have higher boiling points and melting points. So straight away we can eliminate both A and B. So we can eliminate B because it's a transition metal block, this block in the middle, and we can eliminate A because this is also the alkali earth metals, which are still metals and we still would expect it to be able to conduct electricity and things like that. So now we're left with C and D, and if you look at your periodic table, in block C you do still have some metals and these can be part of the transition metal block, and so actually the most likely to find a non-metal in the periodic table would definitely be block D. Okay, so hopefully everyone got that one right. 1.2, element R forms ions of R2 plus and R3 plus. Which section of the periodic table in figure 1 is most likely to contain element R? So we're told that we form these positive ions. So if it's positive ions, we should know that it's going to be a metal. So we look at our periodic table, it's between A and B. And one property we should know about transition metals is they can often form ions of different charges. So here we see that the ions can be 2 plus or they can be 3 plus. And so most likely going to be in the transition metal block, it's going to be B. So 1.3, give two differences between the physical properties of the elements in group 1 versus those of the transition elements. Okay, so the key word here is actually the physical properties. So we don't want to be talking about things like chemical reactivity or anything that actually contributes to reactivity. Now, in terms of the physical properties, one thing we should know straight away is that group 1 going to have much lower melting points and boiling points. Or conversely, you could say the transition elements have much higher melting points or boiling points. And for the second physical property, we could say that group 1, they have much lower density. You could say a variety of things here. Anything that's correct will get you the marks. So other things you could say is group 1 elements are a lot softer, they're less strong, something like that. Okay. 1.4, complete figure 2 to show the electronic structure of an aluminium atom. So here you can use a periodic table. When you look up the periodic table, the number you should notice is the atomic number. The atomic number for aluminium is 13. Now what that means is that it is made up of 13 protons, and if it's an atom, so it's not an ion, it doesn't have a charge, that means it's also got 13 electrons. So now it's just a case of putting these electrons on the shells. So you should know on the innermost shell, you're going to have a maximum of 2 electrons, so you can put 2 there. Then on the other shells, you're going to have a maximum of 8 electrons. So what you do is you fill up these shells in the order like this. So you'd put 8 on the second shell. So that is 1, 2, 3, 4, 5, 6, 7, 8. And then what you say here is at this point you've put 10 electrons on. So on the outer shell, you know you need another 3. So you put 1, 2, 3. Doesn't really matter where you put them, but there you go. That would be the electronic structure of the aluminium atom, just using the fact that we know that it's got 13 electrons. And the next question, aluminium is a metal. Describe how metals conduct electricity. Answer in terms of electrons. So we should know that in a metal you have delocalized electrons. And what we say delocalized electrons, that means the electrons, they don't stay with the atom. They are free to move around, okay? And these electrons, because they have this negative charge, they actually are able to carry the charge. So remember, with electricity, it's all about carrying charge. And so because the electrons are charge carriers, they're able to carry that charge. And the final thing you'd say for the third mark is they can move through the metal. And as a result, therefore, they're able to conduct the electricity all the way through the metal. That's why aluminium would be a good conductor. Okay, so that would be your 1, 2, 3 marks. All right. Next part, 1.6, name the type of bonding in compounds formed between metals and non-metals. So this should be a fairly easy question for everyone to answer. Metals and non-metals, when they bond, they form ionic compounds. Okay, or ionic compounds, or actually the type of bonding, if you look at the question, would be ionic bonding. Okay, but either way, if you've got the keyword ionic in there, you should be enough to get you the mark. Okay, now for the next question, you can see that they've basically linked the previous one. So here we're asked for the type of bonding when you bond a metal and non-metal. Then they give us an example. So now you have magnesium oxide, which is made from the metal magnesium and the non-metal oxygen. Describe what happens when magnesium atom reacts with an oxygen atom. And once again, we're told to refer to electrons in our answer. So this is a type of ionic bonding. So we should know in ionic bonding what would happen. Well, the metal, in this case the magnesium, would transfer 2 electrons to the non-metal, in this case, is the oxygen. And what we can also say is that this would leave a magnesium 2+ ion and an oxygen 2- ion as well. Now this should technically be enough for all 4 marks. Essentially, you can see basically what they'd want in the mark scheme is the idea that you say that the magnesium loses electrons. So you can say here basically that the magnesium loses electrons, that 2 electrons are transferred, and that the oxygen gains electrons. And then you'd also basically say that you form the magnesium and oxygen ions, and that would be your 4th mark. Okay, so that's how you get your 4 marks for this question. And moving on to question 2 now. Sodium carbonate reacts with hydrochloric acid in an exothermic reaction. The equation for the reaction is given there. The student investigated the effect of changing the mass of sodium carbonate powder on the highest temperature reached by the reaction mixture. Plan a method to investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached. You can see straight away there's a 6 marker, so you want to think really about how are we going to structure this question, okay? Or rather our answer to this question. So you want to give a really detailed method, and it's a 6 marker experimental question. So with these questions, you want to give a step-by-step method and as much detail as you can on each step. Step 1, we can say that we want to measure a volume of hydrochloric acid, which is why HCl for short. And the key thing here is a 6 marker, so you want to give detail. How are you going to do this measurement? What equipment are you going to use? So you could say you're going to use a measuring cylinder. Okay, so something suitable. Measuring cylinder would work fine. Then you're going to pour the hydrochloric acid into a polystyrene cup. So hopefully you're all familiar with this experiment, and we don't use a glass beaker here, we use a polystyrene cup in this case of this reaction here. That's because it's a good insulator and we want to measure the temperature change. Okay, then what we're going to do after that, well, we're going to measure the initial temperature. Okay, and again we want to give as much detail as possible. So remember, because we are measuring temperature, we can use a thermometer to do that. So you need to give that detail. Even though it might seem obvious, you need to actually say that you're going to use a thermometer to do that. Step 3, we want to add a known mass of sodium carbonate. So remember, this is the reaction. You're adding sodium carbonate to our hydrochloric acid. So that's your Na2CO3. You can write the whole thing out. I'm just writing it in shorthand now for the video. And again, how are we going to actually measure that mass? You're going to say you're going to measure it using a pan balance or scale. And when we add the mass of sodium carbonate powder, one thing we want to do is we make sure we stir it. And again, this is a key feature of this experiment because we want that reaction to be distributed throughout. So we stir it to also speed up the reaction. Then now we've actually got our reaction going. What do we do once the reaction is going? Well, you can use the question. We want to measure the highest temperature reached. Okay, so we just monitor the temperature and measure the highest temperature reached. And once again, we want to give detail of how we measure that temperature, and it's the same as before. We're going to use a thermometer. Okay, so now we've measured the highest temperature reached for a certain mass of sodium carbonate powder. We want to investigate the effect of changing that mass. So the last step is basically that we want to repeat the experiment with a different mass of sodium carbonate. Okay, so that's what you should say. That should be enough to get you the marks. You might also want to add the fact that you're going to keep certain things the same. So for example here, yes, we're going to repeat the experiment with a different mass of sodium carbonate, but we're going to keep the same volume of hydrochloric acid, which we measured at the beginning, and we're going to keep the same starting temperature as much as we can. So it should be around room temperature. We don't want to start with something really hot or anything like that. And we could also mention that the concentration of hydrochloric acid is also going to be the same. So you could put here concentration as well. Okay, so that should be enough to get you the 6 marks. The important thing here is how you structure it, going in a methodical step-by-step way to give a method for this experiment. The key thing that you're measuring, remember, is the highest temperature reached. So do make sure you mention that. And you notice here with every step, we put in enough detail to say, okay, if you're going to measure something, how are we going to measure it? And that's really important with these 6 markers. So hopefully that was useful, and everyone now knows how to approach these kind of questions. So on the next page, you can see figure 3 shows a line of best fit drawn through the student's results. So you got highest temperature reached on the y-axis and the mass of sodium carbonate on the x-axis. And 2.2 is basically using that graph. So determine the gradient of the line of best fit in figure 3. And it's actually helpfully given us the equation. The gradient is a change in highest temperature over the change in mass. So we can do that here. So we want to work out the change in highest temperature. So we take the lowest temperature over here, the lowest highest temperature if you like, and you want to take the highest temperature over here. What you can do is just look very closely. In our case, we can zoom in. So first thing you want to do with these kind of questions, work out what each square is worth on our graph. Okay, so what is each box actually worth? So you can see between 22 and 24, there's 10 divisions or 10 boxes. So each box is worth 0.2. Okay, so this would be 22.2, 0.4, 0.6, 0.8, 23. 0.2, 0.4, 0.6, 0.8, 24, just like that. And so we can see over here, if you were to get a ruler, we can line this up and see that this is clearly 22.2. 28.2. Next, we take the highest one over here. And once again, we want to take a ruler, draw all the way across. And you should get, so that would be 28.2, 28.4, 28.6 over here. Okay. We'll write that on as well. So that's quite helpful. Then you want to do the same thing for the x-axis to work out the mass of sodium carbonate. So this you can see is just 1 gram, quite helpful. And this one over here, you can see goes to 5 grams over here. Okay, so hopefully now that's clear how we did it. So now we've got the numbers. So 28.6 and 22.2, we can actually just put it straight into our equation. So the change in highest temperature would be 28.6 minus 22.2 divided by the change in mass, which was 5 minus 1. Okay, and if you put that into your calculator, you should get 1.6 as your gradient. Okay, and the last thing here is give the unit. So make sure you read the question carefully. It's worth 5 marks, so you're going to get a mark for giving the unit. So what would the unit be? Well, the units for change in temperature was degrees Celsius, and the units for mass of sodium carbonate was grams. Because we divided the temperature by the mass, then it would be degrees Celsius per gram, just like that. So hopefully that all makes sense how we got to that answer. Question 2.3 then, the initial temperature of the reaction mixture is where the line of best fit would meet the y-axis. Determine the initial temperature of the reaction mixture. Well, again, we want to go back to our graph. It's taught us what to do essentially, is where the line of best fit meets the y-axis. But we can see here, the line of best fit doesn't meet the y-axis at the moment because we didn't have a measurement for a mass of 0 grams. It's impossible to get. But what we can do is basically extend this line back. So what you guys would do, get your ruler out and extend the line back. I'm just going to try and do it like this. And hopefully you have a nice sharp pencil so you can see it really easily. It's not so clear on this one, but I would estimate that one to be at 20.2, 20.4. Okay. And in fact, if you use a slightly sharper ruler, you might get it actually up here. You can see our line is a little bit off. So really you should get about 20.6. So I'm going to go over here and say that the initial temperature of the reaction mixture was 20.6. Because of what I'm doing on the computer is not so easy. That's the method. Okay. You want to extend this line back and see where it crosses the y-axis. 2.4. Another student repeated the investigation but added sodium chloride until the sodium carbonate was in excess. Which sketch graph shows the results obtained when sodium carbonate was added until in excess? So we need to know what that means, what happens when something is in excess. Well, when something is in excess, essentially that means the reaction is complete. We're not able to use any more of it, and it's not actually used in the reaction any longer. So we want to say, what would the graph look like? So we've got a few different options here, A, B, and C, which you can see here quite hopefully. And so in graph A, let's take a look at graph A first of all. So what happens is the temperature increases steadily, and then here you can see there's a big spike of the highest temperature reached, which doesn't really make much sense. If the mass of sodium carbonate becomes in excess at this point, then essentially the reaction wouldn't increase when you add more sodium carbonate, so you wouldn't expect the temperature to increase in terms of the highest temperature that you reach. So this seems a bit strange, so don't think it's this one. Let's look at B then. In B, we just have a straight line. Now this is what we actually got in our experiment, but actually this doesn't show what happens when the sodium carbonate is in excess. If it's not in excess, then we expect that this line will continue increasing, because when you add more sodium carbonate, that means that the highest temperature reached would also increase. Actually, when it's in excess, then the mass of sodium carbonate is essentially at its maximum. It's not going to affect the reaction anymore. And if you look at C, that's exactly what we see. We can see that up to a certain point, when you add more sodium carbonate, the highest temperature reached increases, but after a certain point of adding more sodium carbonate, it's not having any effect on the highest temperature reached. That's because it's not actually affecting the reaction anymore. So over here, we put our answer as C. Figure 4 shows a reaction profile for the reaction of sodium carbonate with hydrochloric acid. And 2.5 will ask, what do labels X and Y represent on figure 4? So label X is over here. This is just a label for the y-axis. And you should know that this is an energy level diagram. And on the y-axis, you're just representing energy. And then label Y is this gap here from the reactants and this line over here. So what is this representing? Well, this is essentially the overall energy change, because you can see here the reactants to the products. That is the energy change. Okay, so we say here the overall energy change. And you should hopefully be familiar with these types of graphs. It's essentially showing what happens to the energy in a reaction. You start off with a certain energy level, you end with a certain energy level. The difference between them is the energy level change. But you can see it doesn't occur linearly. You have this big spike and then drop. 2.6, how does the reaction profile show that the reaction is exothermic? So this is basically what we just explained. What's going on here is you have this big spike in energy from the reactants before it falls to the level of the product. Essentially, energy has been released, and therefore the energy level of the product is below the reactants. So by definition, we can say energy level of products is below reactants. So we started off with more energy in the reactants than the products. We ended up actually losing some of that energy. It's given off exothermically, usually as heat energy, and we end up with the products at a lower energy level. Okay, moving on to question 3 then. This question is about different forms of carbon. So figure 5 represents the structure of diamond. You can see the diagram there. Describe the structure and bonding of diamond, and there's a 3 marker. So you want to put 3 different points. So the first thing we can say is that diamond is a giant structure, okay? It's a giant lattice structure, and you can see the way it's arranged here. All of these atoms are bonded to other atoms in this giant lattice structure. The key thing here is giant. It's not a molecule, it's a giant structure, okay? That's what makes it different. The other thing we can say, these are covalent bonds. So it's covalently bonded. We're talking about the bonding. And we want to give one more point to get the 3rd mark. So what we can say actually is the carbon atoms. It's not only covalently bonded, it's the carbon atoms that are covalently bonded. And each carbon atom is bonded to 4 other carbon atoms. And that should get you the marks. And you can see how it's structured to get you each of the 3 marks. 3.2, explain why diamond has a very high melting point. Well, we can link it back to what we said over here. Why it has a high melting point is to do with the structure. Okay, so you can see here how they're linking one question to the next. And that's really, really common in these exam questions. So what we can say is that diamond has many very strong covalent bonds. These need to be broken in order for it to melt. And because they're so strong, that if you need to break all of these very strong covalent bonds, and there's so many of them, this requires lots of energy. Okay, so that's what you would say for the 3 marks there. 3.3, what is the name of this type of molecule? So you can see we've got a circular structure over here, and hopefully everyone should know that when you have these circular structures, they're called fullerenes. And it gives you here some molecule of carbon 70, so this is a circular structure made of these carbon atoms. These are fullerene. 3.4, molecules such as C70 can be used in medicine to move drugs around the body. Suggest one reason why the C70 molecule is suitable for this use. So suggest keywords, so that tells us there could be lots of different reasons. As long as you give something that's acceptable, you would get the mark. So actually the key reason why fullerenes are used in drug administration in the body is because of this hollow structure. And actually what this hollow structure does is it acts as a cage around the drug. So if you can imagine, you can put the drug inside of the fullerene and it's almost acts like a carrier, okay? But if you put a hollow structure, that would be enough to get you the marks. Again, it's a suggest question, so you could put other things. You could say it's not reactive, so it's not going to react with the body. It's not toxic, it's not going to harm the body if you use it to administer drugs. And it's got a large surface area to volume ratio, and that's to do with absorption. If you put drugs inside your body, you want them to be absorbed. Okay, but any sensible suggestion would get you the mark. 3.5, calculate the number of C70 molecules that can be made from 1 mole of carbon atoms, and it's given us the Avogadro constant over here. Now, students can get confused by this, but actually, if you take it step by step and understand what a mole actually is, it's actually not very difficult, okay? So we're told we've got 1 mole of carbon atoms. Now, a mole is just a number. It's this number over here. It's what they're given to us. 6.02 times 10 to the 23, okay? So if you've got 1 mole of carbon atoms, that means we've got 6.02 times 10 to the 23 carbon atoms. That's all we're saying. The reason why we don't say this number is a little bit long, so we just call it a mole instead. But we know we've got this many number of carbon atoms, and we want to make the carbon 70 molecules. Well, how many carbon 70 molecules can we make? Well, for each carbon 70 molecule, we need 70 carbon atoms. So all we do is we take this and we divide it by 70, and that will tell us how many carbon 70 molecules we can make, because we need 70 for each molecule. Okay, so hopefully that makes sense. Put that in your calculator, you should get 8.6 times 10 to the 21. So you can see it's actually a very simple calculation if you understand what's going on and what a mole actually is. So hopefully that all makes sense now. Right then, question 4, kicking off, we've got a question about zinc and compounds of zinc. Student produces pure crystals of zinc chloride by reacting zinc oxide with hydrochloric acid. So this is crystallization. Hopefully we're familiar with that. It gives us the equation, which will be very useful to us. And one thing you want to note here is in the equation, we're given these state symbols, okay? So these might be useful in these questions. The student adds zinc oxide to hydrochloric acid until the zinc oxide is in excess. So once again, we're dealing with something in excess. Give one observation that the student could make to show that zinc oxide is in excess. So what would happen when zinc oxide is in excess is when you add more zinc oxide, it wouldn't be used up in this reaction. At the moment, the zinc oxide is being converted to zinc chloride. When it's in excess, that means the reaction is basically complete. You've got too much zinc oxide, not enough hydrochloric acid, so it won't react. So essentially what's going to happen is this zinc oxide is not going to turn into zinc chloride, and the observation that you would see is because this is a solid, you'd have some solid remaining, okay? So ordinarily, when you add this solid zinc oxide, it's going to react to form this zinc chloride, which is aqueous. Okay, and this is a liquid, and aqueous means it's dissolved in solution, and liquid means obviously it's a liquid, so you won't be able to see these as solids. As soon as you see a solid still remaining, it's not being converted to this aqueous zinc chloride, that means that it's in excess. Hopefully that makes sense. 4.2 then, why is excess zinc oxide used rather than excess hydrochloric acid? So the key here again is if you look at the state symbols, if you were to use excess hydrochloric acid, this is aqueous. Okay, so this means it's dissolved in water. So at the end, when you want to get rid of the thing that is in excess to just leave you with a product, you would end up having to try to remove this solution from a solution, this liquid from a liquid, which is difficult to do. If instead you have the zinc oxide in excess, because it's a solid, you can just filter it off very easily. So you can say it can be filtered off. 4.3, name one other compound that the student could add to hydrochloric acid to produce zinc chloride. Well, essentially, if we look at this reaction again, what we've got going on here is basically a neutralisation reaction. So you've got this zinc oxide reacting with hydrochloric acid, and this is forming zinc chloride and water. Okay, so you can see the hydrochloric acid is being neutralised by this zinc oxide, which is alkali. Now, essentially, when you have reactions like this, you can use an alkali, a base, or you can use a carbonate. So instead of using zinc oxide, you could use zinc carbonate, or zinc hydroxide would be the basic version. So I'm just going to write zinc carbonate. So those are your options there. Question 4.4, describe how the student should obtain crystals of zinc chloride from a solution of zinc chloride. This is just the crystallization process. So when you have this solution, how do you get the crystals out? So the first thing you're going to do is you're going to heat it until the crystallization point. So you can say until it starts to crystallize, or until the crystallization point. Once you've heated it to the crystallization point, you basically need all the water to evaporate and you leave it to cool down. When it cools down, it basically carries on crystallizing, and when you come back to it when it's cool, then the crystals will be fully formed. Question 4.5 then. Zinc chloride is also produced in displacement reaction between zinc and copper chloride solution. So this is a displacement reaction, really important to note that. The equation for the reaction is given there. Complete the ionic equation for this reaction. So here we want to think about the ions that are present. So we're told that zinc goes to zinc 2+, and with the ionic equations, they always need to be balanced. So what's the other ion going on here? Well, it's a displacement reaction. So what's being displaced is this copper. So you can see over here, we've got zinc 2+, and this is ionically bonded to the chlorine ions to make zinc chloride. Okay, and we know that chlorine, or we should know chlorine makes 1- ions. Okay, I'm going to write that over here, 1- ions. How do we know that? Well, there's a couple ways to know that. The easiest way is to look at the periodic table. Chlorine is in group 7, and so when it forms ions, it always gains 1 electron to have that full outer shell. So it's always going to form 1- ions. We can also tell because we've got 1 zinc 2+ ion to 2 chlorine 1- ions. These have to be balanced. So if the zinc is 2+, then each chlorine has to be 1-. So that's a couple ways to know. Now, if the chlorine is 1-, that means over here it's also 1-. It's a simple displacement reaction. That means the copper at the beginning has to be 2+, for the same reason that the zinc is 2+. So we can write over here, copper 2+. Then what happens to the copper over here? Well, because it's being displaced, what's happened is the copper now has formed a copper atom. And in order to do that, it's essentially gained back 2 electrons, and so we can just write over here is a copper atom. You can just take this straight from the equation. You can see we've ended up with copper over here. It's on its own. That means it's just an atom. Question 4.6, why is zinc described as being oxidized in this reaction? Well, this is an oxidation reaction. This is a redox reaction. There's reduction and oxidation going on here. The reason you can see that is because you can see you've got zinc, which has lost electrons, and copper, which has gained electrons. So it's a redox reaction. And the key thing is here, when something's being oxidized, that means that it's lost electrons. So you can remember your acronym or your rig. Oxidation is loss, reduction is gain. If we say that zinc has been oxidized, we're saying it's lost electrons, which we can see because it's gone from zinc to zinc 2+. So it's lost negative charge, it's lost electrons. Question 4.7 then, zinc and copper can be used with another substance to produce electricity. Complete figure 7 to show how zinc, copper, and another substance can be used to light a lamp. So zinc, copper, and one other substance, some mystery substance. Okay, so essentially we're using this to conduct electricity. So this is all to do with electrodes. So hopefully this looks familiar. If we draw a diagram like this, we have one electrode over here and another electrode over here. And the idea is right now this is an incomplete circuit. There's nothing connecting these 2 electrodes. So one of these will be a cathode, one of these will be an anode. It doesn't really matter. You don't need to know which one's which. So we're just going to label this as zinc, this one as copper because it told us to label it. And the thing that's missing is what's going to connect these 2 together. We're not just going to have a wire connecting it. We actually use a special substance. And we're going to label that substance as an electrolyte. Okay, so another key label to put on your diagram. This is your electrolyte. And this is a substance that basically carries the charge between the anode and the cathode, the positive electrode and the negative electrode, and completes the circuit to allow the lamp to light up. So that's your 3 marks. You can see what you get each mark for. One to label that, one to label that, one to label that. As long as the diagram is correct, you labeled everything correctly, and you've labeled the electrolyte, you would get all 3 marks. Moving on to question 5 then. This question is about groups in the periodic table again. So once again, we want to get our periodic table out so we can have a look at it. The elements in group 1 become more reactive going down the group. Rubidium is below potassium in group 1. Rubidium and potassium are added to water. Predict one observation you would see that shows that rubidium is more reactive than potassium. So what would something look like when it's more reactive when you add it to water? Well, we should know the general reaction of group 1 metals and water. You get this fizzing and bubbling, and you also get a flame sometimes on the water, depending on how reactive it is. Now, what we would see if something is more reactive is essentially, you could say, a more vigorous reaction. But specifically, we want to say, what would we see? So a more vigorous reaction, we see more vigorous bubbling. Okay, that would be enough for 1 mark. Could also say you see a bigger flame, something like that. Okay, 5.2, explain why rubidium is more reactive than potassium. So again, here we'll ask why something more reactive, and that comes down to the chemical structure. Whenever we're asked about reactivity, why something is reactive or not reactive, it always comes down to the chemical structure, particularly the electronic structure. Okay, so that's what you want to talk about. So it's a 3 marker. So the first thing we want to say for our first mark, we want to say the outer shell electron for rubidium is further away. Okay, so remember there's only 1 outer shell electron for group 1 metals, and for rubidium it's further away than potassium. And that's the first point we're going to make. Because it's further away, that means there's less electrostatic attraction. And the key point is the attraction is between the nucleus and the electron. Because remember, the nucleus is positively charged and the electron is negatively charged. And so these are going to be attracted to each other. But the further away your electron is, the weaker that attraction is. And therefore, the attraction is weaker, then we can say that it's going to be lost more easily. And there you see how we lay out our answer very clearly to get each of those 3 marks. 5.3, complete the equation for the reaction of rubidium with water. You should balance the equation as well. Okay, great. So we should know the reaction with group 1 metals and water. This is a general reaction you expected to know. So first thing, we know that hydrogen gas is going to be released. We'll put that there. And we also know that basically you're going to form a metal hydroxide when you react it with water. So you get rubidium hydroxide. And the formula for rubidium hydroxide is just RbOH, like that. Great. Now this is correct, but it's not balanced. So there's 3 markers. So you do get marks for balancing it. So the first thing we're going to try to balance is the hydrogens. So you see on the right hand side, you've got 3 hydrogens. You've got 2 from here and 1 from there. And on the left hand side, you've got 2 hydrogens. So here you've got 3, here you've got 2. So to balance these, essentially what you can do is you can put a 2 in front of your rubidium hydroxide. Remember, you can only put numbers in front. You can't put a number like here. You can only put a number in front. So now you've got 2 hydrogens from here, 2 hydrogens from here on the right hand side. You've got 4 hydrogens. So therefore, to balance it, we can put a 2 in front of our water, our H2O. We'll have 4 hydrogens on the left hand side as well, like that. That's great. Now we have changed the number of rubidiums on the right hand side. We've got 2 rubidiums on the right hand side now, and only 1 over here. So you need to put a 2 in front of here. And the last thing we want to balance is the oxygens. So on the left hand side now, we've got 2 oxygens because we've got 2 in front of here, like that. And on the right hand side, we've also got 2 because we've got 2 rubidium hydroxides. So the oxygens are balanced already, and therefore this is our balanced equation. Next question then, 5.4. The noble gases are in group 0, which is a correct statement about the noble gases. So the noble gases all have atoms with 8 electrons in the outer shell. Now this is not correct. You might think this is correct, but actually when you look at your periodic table, helium is also part of the noble gases, and it doesn't have 8 electrons on the outer shell. It's only got 2 electrons. The noble gases have boiling points that increase going down the group. Now this sounds correct. As you go down the group, the noble gases, they do tend to have larger boiling points. The noble gases have molecules with 2 atoms. This is incorrect. This is actually true for the group 7 atoms. They form diatomic molecules. And the noble gases react with metals to form ionic compounds. So you might think this is correct, but actually the noble gases, the whole idea of them is they're very unreactive. So the one that is correct is actually this second statement here. 5.5. Table 1 shows information about the 3 isotopes of neon. Calculate the relative atomic mass of neon. Give your answer to 3 significant figures. So this is a pretty classic question where we've got isotopes and we want to find the atomic mass from different isotopes. So the way this works is essentially you want to take a weighted average of the different masses in proportion to their relative abundance. Okay, so what we're going to do is we're just going to multiply each of these together and divide through by the total. So we want to do 20 multiplied by 90.48 plus 21 multiplied by 0.27 plus 22 multiplied by 9.25. And then you want to divide through by the total number. And this is percentage abundance, so these all add up to 100 basically. So you can just do divide through by 100. And if you put that into your calculator, you should get 20.1877. But we want to round it to 3 significant figures. It tells us up here and it tells us again down here. So this rounded to 3 significant figures. This is your third one, so you just put 20.2, okay? And that's it for 3 marks. So pretty simple actually if you know how to do it. Okay, this question is about electrolysis, which we've already seen in this paper, but here we're given a slightly different situation where we're told that molten sodium chloride is electrolyzed in an industrial process to produce sodium, and then we can see a diagram of the electrolysis cell that they use. So having a look now, we can see that essentially what's going on is you've got this molten sodium being produced on this end with the negative electrode, and you've got chlorine gas being produced on this end at the positive electrode, and you've got a mesh in between, and you can see you've got molten sodium chloride as the electrolyte. So 6.1, which is the correct half equation for the production of sodium? So here it's kind of given us a clue. We want to produce sodium. So any of these equations that don't produce sodium are not going to be relevant. So here, this doesn't produce sodium, it produces sodium ions. This doesn't produce sodium, it produces sodium ion plus an electron. This one does produce sodium, and this one does produce sodium. So we immediately can narrow it down to 2. Now, if we look at our diagram, what we'll notice is that the sodium is produced at the negative electrode, and that's where it's happening. So essentially, what must happen is you need to have an ion that combines with the electrons at the negative electrode, i.e. is being reduced because it gains electrons, and then it produces sodium. And so naturally, we know that sodium produces positive ions anyway, so we know that it has to be Na+, and it makes sense anyway, because the Na+ would be attracted to the negative electrode, it would then gain the electrons and produce sodium. And so we can see the equation that shows this is this one over here. This one doesn't quite work because the positive sodium ion just seems to produce a sodium atom and an electron, which doesn't really make sense. This one is where you actually gain the electron. 6.2, a mesh is used to keep the products of electrolysis apart. Suggests one reason why the products of the electrolysis must be kept apart. Well, the idea is if you don't keep these products apart, essentially they'll mix, and when they mix, they'll actually react together. So basically we want to prevent reactions, or prevent them reacting and basically reforming the reactants or the initial things, the initial sodium chloride, so essentially to prevent the reverse reaction. 6.3, which type of particle passes through the mesh in the electrolysis of the molten sodium chloride? In this case, you should know that the thing that actually moves across to each of the electrodes is the ions themselves. So i.e. you have the Na+ ion and the Cl- ion, and that's what's actually moving around. 6.4, we've got aqueous sodium chloride is electrolyzed in a different industrial process. Two gases and an alkaline solution are produced. Which two ions are present in aqueous sodium chloride solution in addition to the sodium ions and chloride ions? So which two ions are going to be present? Well, aqueous means that there's water in it. So water we know is H2O, but the water is going to be electrolyzed. The whole solution is going to be electrolyzed. That means it's split into its separate ions. Now we should know that water splits into hydrogen ions, and it also splits into hydroxide ions. Okay, so those are the two ions we're going to get. So that's what we'll write over here. Excellent. 6.5, name the alkaline solution produced. Well, alkaline solutions tend to have hydroxide ions. So what kind of hydroxide solution are we going to produce? Well, we've got sodium chloride, and the sodium is the thing that's going to form positive ions, and the chlorine is the thing that's going to form negative ions. So essentially the hydroxide ions you can see are going to combine with the positive sodium ions, and you're going to get sodium hydroxide. Okay, so that's the answer for 6.5. 6.6, explain how the alkaline solution is produced. You should refer to the processes at the electrodes. So it's giving you a big clue there as to what the 3 marks are for. And why do we get an alkaline solution at the end? Well, essentially, the idea is that what happens at the electrodes? We can start with that. So at the negative electrode, essentially what's going to happen? Well, the negative electrode is going to attract the positive ions. The positive ions we've got is the hydrogen ion and also the sodium ion. But we know that the alkaline solution is produced. So essentially what's going to happen at the negative one is the hydrogen ions are going to be reduced. And when the hydrogen ions are reduced at the negative electrode, and remember we say reduced because they gain electrons. So you can say they're reduced or they gain electrons. Remember, or your rig, oxidation is loss, reduction is gain of electrons. So whenever we gain electrons, we say that the ions have been reduced. So hydrogen ions are reduced at the negative electrode to form hydrogen. So there's now no longer any hydrogen ions left. What happens at the positive electrode? Well, the two negative ions we've got are chlorine and the hydroxide. And remember, we know that sodium hydroxide is left. So we expect the chlorine to be removed from the solution, the chloride ions. So therefore, we know that chlorine or the chloride ions are going to be oxidized, because remember, they lose electrons. So if they lose electrons, we call it oxidation. The chloride ions are oxidized at the positive electrode and they form chlorine. And finally, if those two processes are happening at the negative and positive electrodes, then what's left? The sodium hydroxide is left. So you've got sodium ions and hydroxide ions remaining. And that's what you need to say for your final mark. There's 1 mark, there's your 2nd mark, there's your 3rd mark. Okay, so 7.1, this question is about silicon and compounds of silicon. Now that's going to be true throughout the whole question, so it's just worth noting that at the beginning. The reactivity series sometimes includes non-metals such as carbon, hydrogen, and silicon. Silicon can be extracted by reducing silicon dioxide with different substances. The equation for one possible reaction is given there. You can see they're using carbon. Explain what this reaction shows about the position of silicon in the reactivity series. So what we see here is a displacement reaction because you got silicon dioxide, you react it with your carbon, all of a sudden you're left with silicon on its own, and then carbon, in this case carbon monoxide gas. But it's still a displacement reaction because the silicon has been displaced. So what we can say is that in a displacement reaction, the atom or the element that's displaced is the less reactive one. So we can say in terms of the reactivity series, silicon is less reactive than carbon. And how do we know this? It's because it's been displaced by carbon in the reaction. Okay, so hopefully that makes sense. 7.2, aluminium also reduces silicon dioxide. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper than aluminium. Carbon is obtained by heating coal. Aluminium is obtained from aluminium oxide. Explain why aluminium is more expensive than carbon. Well, it's kind of given us a clue because it just says it's obtained from aluminium oxide. But aluminium oxide is an ionic compound. So to actually split an ionic compound, how do you do it? We already covered it in the previous questions. It's electrolysis. So this requires electrolysis. Now, one fact you should know about electrolysis, it can be quite expensive because you need lots of energy, and that energy obviously costs money. And so because you need more energy because you have to use electrolysis. So that's what you'd say for this question. Magnesium also reduces silicon dioxide. The equation for the reaction is given there. So here we're using magnesium instead. Give one reason why the products are difficult to separate if magnesium is used to reduce silicon dioxide. So we're kind of given a clue with these state symbols here. And if you scroll up to the other equation, there was also state symbols. So what's different between this equation and the equation using magnesium? Well, on the product side, what you'll notice is that these two are both solids, whereas in this one, one is a solid and one is a gas. And so when they're both solids, or they're both liquids, then you can't use filtration. Whereas if one was solid, one was a gas, then just the solid that you're left with at the end would be your silicon. So here it's more difficult to actually separate because they're both solids. Okay, 7.4. Calculate the minimum mass in grams of magnesium needed to completely reduce 1.2 kilos of silicon dioxide. And we're given some atomic masses there. So this is a 5 marker. So you want to go nice step by step to work this one out. So the first thing we want to work out is how many moles of silicon dioxide do we actually have? Now to do that, we need to work out the molecular mass first of all. So given the atomic masses, and we know the formula for silicon dioxide because it's given to us in this question, SiO2. So we want to work out the molecular mass of SiO2. And that's going to be equal to the atomic mass of silicon, so 28, plus 2 times the atomic mass of oxygen, so we've got 2 oxygen atoms. So 16 times 2. And you can put that into your calculator, you should get 60. Then now we've got the molecular mass and we've also got the actual mass of 1.2 kilos. So the formula that relates these together is the mass is equal to Mr. moles, or MR multiplied by moles. So we want to work out the number of moles, so we can rearrange for moles is going to be equal to the mass over the MR. So the mass is 1.2 kilograms, but in this equation we need it in grams. So we need to convert it to 1,200 grams and divide it through by the MR, which we just worked out was 60. And when you do that, you should get that the number of moles is going to be 20. Okay, great. So now we know we've got 20 moles of silicon dioxide. How many moles, therefore, of magnesium do we need to reduce 20 moles of silicon dioxide? So we need to go back to our equation. And what you'll notice is that for every mole of silicon dioxide, we've got 2 moles of magnesium. So it's a 2-to-1 ratio. So if you have 20 moles of silicon dioxide, that means we need 40 moles of magnesium. Okay? So now we know we need 40 moles of magnesium. And we also know the MR of magnesium because it's given to us as 24. So you can write that over here. And once again, we're going to use our same equation, mass equals Mr. moles. And this time we don't even need to rearrange it because we're looking for the mass. So now the mass be equal to the MR of 24 multiplied by the number of moles. And we know that it needs to be 40. And so 24 times 40 should give you 960. And so the mass of magnesium is going to be 960. And the unit is grams. So you can put that over here. And that's the minimum mass because some of it will be lost. Okay, so that's how you work that one out. And you can see if you go step by step, hopefully it's quite a simple process if you know what you're doing. Okay, 7.5. Si2H6 is a covalent compound of silicon and hydrogen. Complete figure 9 to show the outer shell electrons in a molecule of Si2H6. Well, the key thing here is that it's a covalent compound. when things are covalently bonded, they share electrons. So we need to show that in our diagram. So I'm going to actually zoom in a little bit. So when we have a covalent bond, they share a pair of electrons. So let's take this first one here. There's going to be an electron from the silicon, and there's going to be an electron from the hydrogen, which I'm going to represent like that. So that would be one bond. There's going to be one here as well. So we'll do it like that. There's going to be one more here because, again, another hydrogen. And the exact same thing for the other atom of silicon. There's going to be an electron from the silicon in each of these bonds and one from the hydrogen as well. And then for the last one here, you'd also need an electron from each of the silicon atoms because they are also bonded covalently together. Okay, so that's how you complete the structure like that. Okay, question 7.6 is quite a demanding one, so we'll go nice and slow so everyone can follow, hopefully. So we are told that the Si2H6 reacts with oxygen, and we're given this equation, so take note of this, it's very important. 30 centimeters cubed of Si2H6 is reacted with 150 centimeters cubed of oxygen, and this is an excess of oxygen, so not all of the 150 centimeters cubed is going to react, okay? Calculate the total volume of gases present after the reaction. So volume of gases and after the reaction. And we're also told that all volumes of gases are measured at the same temperature and pressure. Okay. Now this is important because that means that we can essentially use the ratios here to work out the volumes of gases that will be used in the reaction and produced in the reaction. So if we're told that 30 centimeters cubed of Si2H6 is reacted, then we know that according to our equation, there's a 2:7 ratio of Si2H6 with oxygen. Okay, so therefore to find the amount of oxygen that's actually reacted, the volume of oxygen, we just take that 30 centimeters cubed and we multiply it by 7/2. And this should give us 105 centimeters cubed. So 105 centimeters cubed of oxygen is used up in our reaction. Okay, so let's make a note of that. This is important because we want to keep track of all the gases that are being used and produced to work out what's left at the end. Okay, so now we know how to do it for oxygen. We can basically apply that same technique for the product, so the silicon dioxide and also the water. So the water is the one we're interested in because this is the gas. Okay, so we kind of ignore the silicon dioxide, to be honest. We can see that for every 2 moles of Si2H6 you produce 6 moles of water. So therefore you can basically use the same technique. So the 30 centimeters cubed of Si2H6 multiplied by 6/2, because this time it's a 2:6 ratio. 6/2 is just 3, so you should get that you end up with 90 centimeters cubed of water produced. So again, I'll make a note of that. So essentially now you've done most of the calculations that you need to do. You've worked out that 105 centimeters cubed of oxygen is used up and 90 centimeters cubed of water is produced. The last gas is actually the Si2H6 itself. But the important thing is this is reacted in excess with oxygen. So this is the limiting factor. So all of the Si2H6 will be used up. So we can ignore basically this 30 centimeters cubed. Okay, this is all going to be used up by the end of our reaction. So what are we left with at the end of our reaction then? Well, essentially we've produced 90 centimeters cubed. We had the initial 150 centimeters cubed of oxygen, and we need to take away from that 150 the 105 centimeters cubed that was used up. And so if you basically add all of those together, you should get that the final volume of gas is going to be 90 plus 45 or 135 centimeters cubed of gas. Okay, so it's a little bit confusing, but essentially the key step here is to realize because all the gases are measured at the same volume, all the volumes of gases are measured at the same temperature and pressure, we just want to use the ratios in the equation that's given to us. And then we just need to keep track of things that are being produced, things that are being used up. And when we do that, then we can solve for the volume of gas that's left at the end quite easily. Okay? Okay, and question 8, the final question for this paper. Let's go through it. This question is about acids and alkalis. Explain why the pH of an acid depends on the strength of the acid and the concentration of the acid. So we want to explain these two aspects, and it's worth 4 marks. So probably 2 points for each. So the first thing, let's deal with the strength of the acid. So when you have a stronger acid, what does that mean? Well, that means when an acid is stronger, so a strong acid compared to a weak acid, essentially what happens is the hydrogen plus ions or the H plus ions dissociate more strongly. And this is important because the pH depends upon the H plus ion concentration or the hydrogen ion concentration. So if you have a higher concentration of hydrogen ions, that means your pH is going to be lower. So we can also write that. You get a lower pH. Remember, stronger acids have a lower pH. So therefore, that's kind of the stronger acid one explained. Why the pH depends on the strength of an acid. Remember, stronger acid, hydrogen ions dissociate more, therefore your pH will be lower because pH depends on the concentration of hydrogen ions. We can actually add concentration here. Okay, so now let's do the same thing for the concentration of the acid. So when you have a higher concentration of acid, what that means is you have more acid in the same volume. So essentially more acid or more solute in the same volume. And therefore you have a higher concentration of hydrogen ions. Just like before, when you have a higher concentration of hydrogen ions, that means you have a lower pH, because remember we just said the pH depends on the concentration of H+ ions. Okay, so that should be enough for the 4 marks. 8.2, a student titrated 25 centimeters cubed of hydrochloric acid with a 0.1 mole dm cubed barium hydroxide solution. And we're given a table here. The student calculated the volume of barium hydroxide solution to be used in the titration calculation as 23.5 centimeters cubed. Explain why the student used a volume of 23.5 centimeters cubed in their titration calculation. Basically, where did that number come from? So with any titration, you're going to have lots of different numbers because you do repeats. You should spot straight away 23.9 is an anomaly. So how do you get 23.5? Well, essentially you calculate a mean, and that would be enough for 1 mark. But the second mark, basically you need to allude to the fact that 23.9 is not used in this calculation. So therefore we want to calculate a mean using the concordant values. And concordant values means basically all the values, not including the anomalies. And that would be enough for the 2 marks. 8.3, 25 centimeters cubed of hydrochloric acid reacted with 23.5 centimeters cubed of 0.1 mole dm cubed barium hydroxide solution. And we're given the equation as well. Calculate the concentration of the hydrochloric acid in moles per dm cubed. Okay, so it's worth 4 marks. So again, let's go step by step to solve this one. So the first thing is we're given the volume and the concentration of barium hydroxide solution. So we can use our equation that the moles is equal to the concentration multiplied by the volume. And we're going to use that to work out the moles of barium hydroxide solution. Okay, so if we had 23.5 centimeters cubed, then we want to multiply that by the concentration. But the concentration, the key thing, is given in moles per dm cubed, and our volume is centimeters cubed, so we need to convert first. So we're going to convert the centimeters cubed to dm cubed. So we do that by dividing by 1000, and then we can just plug this into our equation, concentration times volume. So this is our volume, so let's multiply it by our concentration, which was 0.1 moles per dm cubed. And when you put that into your calculator, you should get an answer of 0.00235 moles. Okay, so this is the moles of barium hydroxide. So let's actually label that. Now we need to look at our equation again, and what you'll notice is that for every mole of barium hydroxide, you need 2 moles of hydrochloric acid to neutralize it. So therefore, if we have 0.00235 moles of barium hydroxide, that means we have that multiplied by 2 moles of hydrochloric acid. So if you multiply that by 2, you should get 0.00470 moles. And this time it's the hydrochloric acid that we're looking at. Okay, so let's label that as well. Okay, great. So now we've got the moles of hydrochloric acid. We are asked to work out the concentration. So at the beginning of our question, we were given the volume, 25 centimeters cubed. And again, we're going to convert that to dm cubed and then use our equation that we started off with. So to get the concentration, you need to rearrange. So concentration will be equal to the moles divided by the volume. And the moles we know is 0.00470. And the volume was 25 centimeters cubed, converted to dm cubed. So 25 divided by 1000. And you could put that into your calculator, or you could basically, when you divide by a fraction, it's the same as multiplying by the reciprocal of that fraction. So you can flip that. But either way, you should be able to work out what that is. And when you put that into your calculator, you should get 0.188 moles per dm cubed. Okay, so hopefully everyone got that right. You can see again, it's not that tricky. Another student titrated sulfuric acid with barium hydroxide solution. The equation for the reaction is this. The student measured the electrical conductivity of the mixture during the titration. The better conductor, the higher the electrical conductivity value. And figure 10 shows the results. Explain why the electrical conductivity of the mixture was 0 when the sulfuric acid has just been neutralized. So it's just been neutralized. Why would the conductivity be 0? Refer to ions in your answer. So again, we're given a clue as to the answer. When you have a mixture like this, what you'll notice is that this is an aqueous solution of ions. Now, when you have a solution like that, essentially the things that carry the charge are the ions. Now, what happens when you neutralize something? Well, in this case, when you neutralize it, you actually remove the ions from the solution. So what we can say is there's no ions free to move. The ions have reacted, so there's no ions free to move. And therefore carry the charge. And this is because the barium sulfate is insoluble. Essentially, the barium sulfate is solid. So when after you immediately neutralize it, you're going to be left with this barium sulfate, and this is solid, and you're going to be left with this water. And so essentially, you've used up your hydrogen and hydroxide ions to produce water, and water itself won't be able to carry the charge. Okay, so that's what you'd say for your 3 marks. 8.5, the student then added a further 10 centimeters cubed of barium hydroxide solution. the electroconductivity of the mixture increase? Give one reason why. Well, now we've added barium hydroxide solution. Barium hydroxide is an ionic compound. So what you should be able to say is now you've got barium ions and hydroxide ions that are free to move and therefore carry the charge and therefore conduct the electricity. Okay, so that's the last question in that paper, the end of the paper. Hopefully you guys found that useful. If you want to see more of these kinds of papers, please let me know in the comments. Please do also subscribe so you can stay tuned when we upload more papers. Okay, I'll see you in the next one.